Maximum minimum using algorithm. Determine the absolute maximum minimum value of the function f of x equals to x cubed minus 3x squared, where x is greater than or equal to minus 2 and less than or equals to 1. Illustrate your answer by sketching the graph. Now, let's understand a couple of things here. That is, first thing, what is this algorithm? And then, where can it be applied? So we have an example here. So let me write down the example first, which is f of x equals to x cubed minus 3x squared. And here, the constraint is that x is in between minus 2 and 1, and both included. So it's a closed interval. Now this algorithm for finding maximum minimum is actually applied in closed interval itself. So that's a good thing. So first thing is where it is applied and when. So it is always applied in closed interval as given here, right? So in the interval given to us, let me explain with reference to the given question. Now how to find absolute maximum minimum? So first step here is to find critical number. Now critical number is a point on the graph where the derivative of the function, let me write f dash x, is equal to 0 or it does not exist. So both are critical numbers. I've seen some ambiguities in this definition. At times in books they omit does not exist, but for me it is an important criteria, since many graphs with like absolute function, right, it has a minimum here and f dash x will not exist, right? Similarly, in radical exponents, we'll have cusps and corners, correct? There also will have absolute maximum or minimum, for example, like this, right? So in those cases, we'll not be able to apply this definition if we omit that part, right? So we will keep this for the time being, and you can discuss with your teacher about this in case there is ambiguity. Okay, but critical number for me is where the derivative is either 0 or it does not exist, right? Now in a closed interval like this we have now in the closed interval like this we have there will be absolute maximum or minimum in either f of minus 2, the lower bound, or at f of critical point, let me call this critical number as c, f of c, or at f of 1. So those are the points which you have to check for. Just evaluate their values. Whichever is maximum, that is absolute maximum. Whichever is minimum, that is absolute minimum. This algorithm is extremely simple and very helpful. Now let's apply this and see in our context. So first step is, let's find the derivative here in order to find critical numbers. So we get 3x squared minus 6x, and this could be factored, so we get 3x and we're left with x minus 2. So the critical number here is at, let's say, critical number. Let's find. So for finding critical number, we need to have f dash x equals to 0 or does not exist. In this case, it could be 0, right? So for f dash x equals to 0, the factor 3x could be 0 or x minus 2 could be equal to 0, right? So f dash x equals to 0 means this is equal to 0. And that is possible at x equals to 0 or at x equals to 2, right? So we have two critical numbers here. Now out of these two critical numbers, what we notice is our restricted domain is from minus 2 to 1. So only one qualifies, which is 0. So we have to consider this critical number only, right? Not the other one. So now, using the algorithm, we will try to figure out where do we have absolute maximum and where is it absolute minimum. So we'll evaluate the value of the function at minus 2, one of the boundaries, at the critical number, which is 0, and at the other boundary, which is f of 1, right? So you can use your calculator to evaluate this point, right? So So we can evaluate, we just plug in the values here. So if you put minus 2 here, you get minus 2 cube minus 3 times minus 2 square, which is minus 8, and 2 square is 4, and 4 times 3 is 12, so minus 12, and you get minus 20. And for 0, you get 0, right? And for f of 1, you have to plug in 1 here, so you get 1 cube minus 3 times 1 square, so you get minus 2. So clearly from here, we get a maximum and a minimum value. So the maximum value, since these are negative, is right there. So that is the maximum for us, and the minimum is minus 20. So that becomes the minimum value for our function, correct? So that is how we can actually get maximum and minimum values for the function, correct? Have a good look at it. And now let's try to graph it and see how does it look like, correct? So let's have a graph here, and as we see, you can actually factor this. So let me write down the factored form of the equation. So let me put it right here, which is f of x equals to, so let's factor out x squared. When you factor out x squared, you get x minus 3. So you have a 0 here, and you have 0 at 3. Now the function is with positive leading coefficient, so you can sketch it. It will go, is it degree 3, it will go from here and right there. So you can go like this, correct? So that is your function. Okay, so minus 20 is at minus 2. So we will have this. Okay, so let us say this is minus 2, and this point here is minus 20 for us, correct? And then we have a maximum here, which is at 0. And then at 1, we have value at, this is 1. And at value at 1, we have minus 2, right? So that minus 2 happens to be a much lower value as 0, but it is higher than the value at minus 20. So from here, you can clearly see that we do have a maximum at 0 within this interval. So we're considering this interval. Don't consider the rest of the graph. Just consider this interval, okay? So a section of the graph we're looking at. So when you look at the section of the graph, there is the maximum, and this is your minimum, correct? So that is how you get maximum minimum in a closed interval, correct? Normally, xq function will not have absolute maximum because it extends till infinity, right? Nor will it have absolute minimum because it is from minus infinity to plus infinity. But when you're considering a section, when you're considering a restricted domain, in that case, you will have absolute maximum minimum as is being demonstrated here with the help of diagram. I hope the concept is absolutely clear, and now we'll move on with some interesting word problems using this algorithm and finding least, maximum, minimum such values. Okay, thank you.